And I present to you Dino Zovi.
Thank you. My name is Dino Zovi. You might remember me from other past hits such as blah, blah, blah. Actually, I'd like to thank everyone for being here today. This actually makes 10 years since my first presentation in Vegas, way back at DEF CON 8. So I've been talking about how to exploit memory corruption issues for 10 years now, so it's kind of a little crazy. So let's see how things have changed. So today, I'm going to be talking about return-oriented exploitation. And what this does is this actually is meant to encompass a variety of techniques, with going back to the basic return to libc, as well as the newer, flashier, trendier return-oriented programming, which is now still about like 3 years old. And one of the things I want to point out is that actually I'm not going to be talking about any new techniques in this talk. So I'm not going to be revealing anything, very whiz-bang. But what I hope to show is that 3-year-old techniques are enough to own IE8 on Windows 7. And here's how. In particular because if you start looking at like return-oriented programming, a lot of this flashy stuff, a lot of people try to make it look more complicated than it is and have gone through and written compilers and all this stuff. And whereas my infrastructure that I'm going to be talking about is I deliberately took the simplest implementation possible at every turn so that I finished my script in one weekend, and 2, just to kind of show that this is the level of exploitation defense these days, is that it doesn't require really bringing a lot of force to bear. So let's kind of give a little context to why this is necessary. So way back in the dark ages, also known as a few years ago, if you had full control of the EIP register on, I'm going to be talking about x86 the whole time, so we can just assume that. If you had full control of EIP, you were just really close to arbitrary code execution. However, now with exploit mitigation such as DEP, ASLR, non-executable memory, full control of EIP is sort of just one step in the stage to getting a payload running. And so this stage between full control of EIP and running your Metasploit payload or whatever is the return-oriented exploitation stage. And so what this means is that attackers now must identify supplemental vulnerabilities or other issues in order to enable the exploitation of the memory corruption vulnerability that they found. And what these issues are memory address layout disclosure vulnerabilities. Some people call these memory leaks, but unfortunately that kind of collides with what programmers call memory leaks. So it's kind of like a memory information leak is another good term for it. And the other issues you can find are the availability of known executables. If you know that a certain version of a certain DLL is always loaded at a fixed location in memory, you can use that as material for your return-oriented exploitation stage to get your payload running. And so some of the options here are 1, find DLLs that don't opt into ASLR, whether these are third-party or whether these are built into the operating system. 2, you can use something like a JIT spray, which lets you just spray the heap with executable code that you can partially control that will allow you to bridge to your shellcode. Or kind of the older, about 2 years ago, Mark Dowd and Alex Sotorov presented a way of using .NET user controls in IE to place executable code at a fixed location in memory. So any of these types of issues are now required to exploit memory corruption vulnerabilities on a modern operating system like Windows 7. So what I talk about today is give a little more background on where exploitation came from and where we are now, give more detail on what I call return-oriented exploitation, and talk about my toolkit that I call BISC, which stands for Borrowed Instruction Synthetic Computer, or actually the C word actually kind of changes. Sometimes I do computation, sometimes computer, whatever I feel like when I'm making the slides. Or the alternate title is ROP in Evenings and Weekends, showing how easy it actually is. And I'm going to talk about how we can use these kind of type of toolkits to enable exploitation. I call these the return-oriented exploitation strategies, how you can enable arbitrary payload to run. And then I talk about how you can use this to exploit Aurora on Windows 7, and I'll do the obligatory demo where I will show a web browser, click a button, everyone sees a calculator, and we clap. So we're all on the same page with that? Cool. And then I'll try and draw some conclusions from that. So where are we today with exploitation? with memory corruption exploitation, it's one of these things that just never dies, because everyone, I mean, like I've talked to so many people, for a long time that have always said, we assumed this would be over in the early 90s, and then people were still doing it in the late 90s, and people were like, after 2000s, we're still going to, buffer overflows will be dead, and then after DEP and ASLR, buffer overflows will be dead. Well, the traditional buffer overflow may be dead, but memory corruption issues are still very much here. They just kind of change. And if you actually look back at the decompiled Morris worm, you will see that the way that it executes, the way that it does the buffer overflow for the finger D, despite some descriptions that were wrong, mostly because it was space alien technology that fell in people's lap and they had no idea what this was. But basically, if you look at it, it's the exact same formula as Aleph 1 published 8 years later in FRAC. Basically, what you're doing is you're writing machine code by hand, and that's your shell code, and it executes the execve system call with bin.sh to give you a shell. And basically, you put a bunch of nops before it just because you don't know exactly where on the stack it'll be, and you overwrite the return address with the address where you think will be in the middle of your nops. So it's basically it's been the exact same thing for like those 10 years. And this technique, which was lost to time, was rediscovered by Thomas Lopatic in February 1995 and published a bug track in how he exploited a stack buffer overflow in NCSA HTTPD. And he was kind of working through it, and he's like, oh, you can do this and do this. And he wasn't really aware that he was doing basically the exact same thing, but for a different architecture that Robert Morris had done years before. But finally, with the FRAC article by Aleph 1, kind of was democratized. People started finding these bugs everywhere. And we're like, all right, stack buffer overflows, those are a problem. We just got to find all those and we'll be good. But then we learned that, no, actually not just stack corruption was exploitable, so was heap corruption. And so another piece of space alien technology fell from outer space, and this was Solar Designer demonstrating how to exploit heap buffer overflows by overriding the next and previous pointers of freed chunks in the heap. And this kind of took a lot of people by surprise, and all of a sudden heap buffer overflows are exploitable. And even around this time, there were academic projects. For instance, I remember seeing one that would take all stack allocations and put them onto a heap, and they said because heap exploitation is not exploitable. That came out like a few years after this. It's like, you should read bug track. And then we said, all right, heap overflows stack and heap buffer overflows are the problem. Then integer overflows happened. And these weren't overflows in the traditional sense. They were more integer wraps that would cause a buffer overflow later on. And so then we started looking for these in a lot of web servers, a lot of other things like that. And so now basically this is pretty obvious stuff. We found that these bugs are everywhere. Worms destroyed the internet. Somehow we're all still here and still using the internet. But this caused one of the biggest corporations to take a big turnaround and actually say, all right, we need to get these out of our code. We have the SDL. And the SDL has in my mind, three main pillars. One, secure coding. We need to make sure the quality of the software we write is robust, and it's high enough quality to eliminate vulnerabilities before they're written. Two, we need to audit our source code before we ship it. We need to, if there are any vulnerabilities that have been written, we need to actually find them before we ship them. They end up on a customer's system. And then, just in case there are latent vulnerabilities, because theoretically that can happen, there will be exploit mitigation technologies that will make exploitation of those more difficult. And so the exploit mitigation actually is a pretty important thing, because it is an acknowledgement that we can't actually find and fix every single vulnerability. And especially with client-side applications, if you look at, I think Charlie Miller's recent talk, a lot of the bug mining talks that were going on today, they're talking about how they have 60,000 crashes, and maybe 10,000 of those are exploitable. And if you think that the winning strategy is to report, patch, and patch each of these vulnerabilities, that's not ever going to happen. So for these client-side applications. So in my mind, exploitation mitigation is and privilege isolation, sandboxing, all this stuff is kind of the better way forward. And so exploit mitigation that was implemented in Windows XP SP2 was sort of the first acknowledgement of this. And this included a number of things. And the number of mitigations that have been included in modern operating systems, such as Windows, have increased with each release. And what this does is this makes exploitation more difficult. Each mitigation forms a tapestry that will eliminate or make exploitation of certain types of vulnerabilities more difficult. And this protects the stack, the heap, exception handlers, random executable memory, and so on. And what this does is this basically winnows down the situations that are exploitable. And so if you have, if modern day and age, you find just a vanilla stack buffer overflow, a stack cookie will effectively make it impossible to exploit. So the technique of return address overwrite, boom, that's kind of dead now. And now with heap protection and safe unlinking and all those technologies, overwriting the heap metadata on a free block, well, that's no longer exploitable. Then attackers sort of move on and iterate to the next technique. They discover another technique. It gets mitigated, and we sort of do this dance. Where we are right now is near the bottom at the application-specific data overwrite, because DEP and ASLR have sort of mitigated a lot of the other things. And now what's common is overwriting C++ vtables, which are application-specific, and overwriting the function pointers there. One of the things to keep in mind with these mitigations is that they actually require cooperation between a lot of parties. And this is actually where a lot of applications fall down, because they'll include old code, new code, third-party plugins, and not everyone may use the same compilers and same flags, so you won't get all the best mitigations. And because there's some that require cooperation from the operating system, such as heap protection, SEH chain validation. And there are others that require recompiling your code, such as stack cookies, safe SEH. And then some others that require the application to opt in. Even though they are provided by the operating system isn't going to force it on every application. So DEP and ASLR in particular on Windows need to be opted in by the application. And for end users, like if say you're like an IT administrator and you're building like a golden build for enterprise, it's actually somewhat difficult for you to go through and find what mitigations are active in your configuration of Internet Explorer. You need to look at what plugins do I have installed, is the application compiled to safe SEH, do all the modules, opt into DEP and ASLR, is it running with DEP or permanent DEP, is it possible to load modules that don't opt into ASLR or DEP through a variety of means? All this stuff is possible. And if you look at what some might consider the gold standard, we look at IE8 on Windows 7. This is all Microsoft code, this is all should be safe. Well, it uses the complete suite of exploit mitigations, but still that's unfortunately not enough. Because if you install any third-party plugins, there's a chance that one of them will have a module that doesn't opt into ASLR. And there are a number of common plugins that have have DLLs loaded at fixed locations that an exploit developer can use to basically to bypass DEP and ASLR using the things that I'm talking about here. And there are even ways to do this without any third-party plugins. If you're interested in that, I believe a researcher, Shaibao Chen, is presenting that at XCon next week. So unfortunately, Blackhat didn't accept his talk, but it's some pretty cool work, so you should check it out. So let's talk about return-oriented exploitation. So now, having full control of EIP is not direct arbitrary code execution, because you used to be able to jump straight to your code or do kind of a little more clever things like a register spring, where you jump to some code that will go indirectly through a register to your code. Now that you have ASLR or library randomization on Mac OS X, which is a kind of a knockoff version of ASLR, you're not going to be able to do this. So even EIP pointing directly to data that you control will not give you arbitrary code execution, because DEP or NX will make that memory page non-executable. And if you're looking at like embedded systems like a mobile phone, you might have issues like, for instance, the ARM has separate instruction and data caches. And so your payload might be in the data cache, and when you tell the processor to go execute this memory, it'll fetch data from main memory, not your shellcode from the data cache. So it's kind of tricky. So what you need to do is turn EIP control into arbitrary code execution. And so it requires a little extra steps. The first step is the stack pivot. And what you're going to do is you're going to leverage full control of EIP to get full control of the data pointed to by ESP. And once we have control of the stack data, we're going to use this to control execution to then give us enough control to have full arbitrary code execution again. And this is the return-oriented exploitation step. Go back. All right, so this first step is called the stack pivot. Or some people call it the stack flip. I call it stack pivot. Same thing either way. And what you're doing is you need to get ESP to point to data that you control. In the vanilla stack buffer overflow from our days of yore, you got that for free. Well, now you have to pay for it. So what you need to do is find a simple instruction sequence that'll point ESP into data that you control. And there's a number of ways you can do this. You can find something that, wow, my machine is lagging like crazy. You can move Yeah, move a register that you control to the stack pointer and then return. You're probably not going to find this very often. You can find an instruction sequence that'll adjust the stack pointer by a constant amount. That's also kind of rare to find one that you really like. My favorite here is the exchange EAX ESP followed by a ret, because it's a pretty short encoding. Anyone tell me how many instructions that encodes to? I see a 2 in the audience. That is correct. So basically, the 2-byte sequence, hex 94, hex C3, actually is amazingly common in Windows DLLs. And so it's pretty common that you'll find this sequence be able to get you, if EAX points to data that you control, which is pretty common as well, it'll get you right to your stack pointer pointing to data that you control now. And once you have control of the stack, that contains a return-oriented program, and or I'll say return-oriented exploit payload. And what this can be is either a full payload that does everything return-oriented, which is a lot of work. You probably want a compiler to help you do that, or you can do what I do, which is just make a return-oriented payload stage, which is just a small amount of code that will just make it so that you can execute your normal payload. So let's kind of review a little bit, just get in this right mindset. Let's go back to 1997, return to libc. This was, Solar Designer described this technique and named it right after a number of systems, including Solaris, started implementing non-executable stacks because, of course, people believe that the root of the problem was executable code on the stack. Well, if all the libraries are loaded at known places, what you can do is, at least on x86, return to a function, and you abuse the fact that return to a function in that shared library. And what you do is you abuse the fact that on x86 the function arguments are taken from the stack as well. And if you've already overwritten the stack, that function that you jump into will use the arguments from your controlled data. And what this effectively does is simulates a function call to that function with arguments that you control. So an example of that is you can call system and give it the address, give it a pointer to a string that you control. You can kind of find that in your environment, or you can do a number of things, and that'll essentially give you, let you execute a arbitrary string from the shell with just one return. And what's cool is you can even chain these together. So you can extend this technique a little bit, and because the stack unwinds upward and you've already overwritten a lot of it, you can simulate one function call and then another function call and then another. And the only thing that's difficult to do is to use the return value from one function as the arguments to the other. We're going to need some a little more advanced technique for that. But with that, if you don't need to do that, you can easily do this return chaining. And what you do is basically you just lay out the stack in a certain way that allow you to advance the stack pointer and kind of fix things up. And I'll kind of show you how this works. So if you look on the left, I'm going to show you kind of the assembly code that's executing. On the right, I'm going to show you the diagram of the stack, because everyone loves stack diagrams. And I love making them, because I made like 100 of them for this. And you can see I'll have it highlighted where the actual stack pointer is pointing to and what data will get used. So first, we've executed a return. We've corrupted the stack, and we're executing a return that's using our chosen return address. And that takes us to the top of this function in a library. And it's going to use the standard function prologue that's going to save the frame pointer and so on. And eventually, it's going to use our arguments, which is pulling, again, from the stack that we control. And then as it's leaving, it's going to restore this frame pointer and then pop the next element off the stack, which is going to be the address of a small sequence of a pop-pop-ret, that what we're going to use is to skip over the arguments on the stack so that we can realign the stack to our next fake stack frame to simulate the next function call. So it's going to skip over those and then call our next function. So that's basically how it works. So we all know all this. This is all very old. So let's go a little less old. Return-oriented programming is the name given to a technique that was published by Hovav Shakam in 2007. And the main idea here, which was instead of returning to the top of a function, let's return to random bytes in the text segment just out of sequence. And what we'll find is that because x86 allows unaligned instructions, there are many unintended instruction sequences in legitimate instructions. And actually this is an older technique that was a little lesser known called the borrowed code chunks technique by Sebastian Kramer. I think he did it in 2005, but I have that reference later on in my presentation. But here you can see the main idea is that assume an application actually has the instruction of moving this 32-bit constant into EAX. And that encodes into the 5-byte instruction sequence that you see below. Well, if you just skip the first byte and return to the last 4 bytes, what happens is this turns into the instruction sequence that stores EAX into ECX plus 8 and then returns. And this is the main idea here. We can find unintended instruction sequences in legitimate instructions. And all we need to do is find these unintended sequences in anywhere in executable memory that we know where it is. That's at a static or a known location. So another way to understand this, to give credit to Dr. Raid's girlfriend, because Dr. Raid was writing a script to do this, and he explained it to her, and she's like, wait, that's just like a ransom note. And we're like, that's genius. Yes, exactly. So return-oriented programming is a lot like a ransom note. You're going through the newspaper, you're cutting out letters, and those are the unintended instruction sequences, and then you're combining them into words, and these are your return-oriented gadgets, to use the terminology. And then you combine those gadgets into an actual letter, or actual note, and that's just like your return-oriented payload. So it's a really great way of explaining it. And to explain what a gadget is gadgets are ways of combining these unintended sequences along with data on the stack to perform a sort of higher level semantic action. So, some things that might be an example of a gadget is a sequence that will write a chosen 32-bit value to a chosen memory address, or another sequence that will do arithmetic operations on a piece of memory, or a sequence of returns that will actually simulate a function call. And basically what you're going to do is you're going to write your program out of these gadgets. So here's an example gadget here. So if you have 3 sequences, here's how we're going to combine them. The first one, you have a pop EAX ret that'll set EAX to a chosen value. Second one is a pop ECX ret that'll set ECX to another value. And the third one will store EAX into the memory address pointed to by ECX. And then now we have a store immediate value, or if you're an old Commodore 64 programmer, you think of this as a poke. Kind of here's basically how it works with yet another stack diagram. We're going to return pop EAX to dead beef, return again. Now we're going to set ECX to feed face. And then when we return to our third sequence, we're going to write dead beef into feed face. And return, and go on. So you can see how basically you can combine these gadgets actually perform useful things. Once you have these gadgets, you can do higher level computations. And this is what's been called a return-oriented program. And the idea here is you can actually write a compiler for this. And this is what the Havav Shakam's paper did. And the innovation there is he actually made it Turing complete. And so he has conditionals, he has loops, and he actually wrote a full C compiler and demonstrated that he could compile quicksort against the Linux libc. And so quicksort would be implemented by a bunch of random returns into libc, which is pretty cool. And there's been actually a lot more interesting work, such as the name's escaping me, but some other researchers, I think from Germany, at Usenix in the last year or two, presented a paper on writing a fully return-oriented rootkit, basically where they could implement traditional rootkit technology using only returns into loaded modules. And this kind of dispels the notion that like a rootkit has to involve hidden code in your kernel. Well, it's only using the code that's there. And the quote that actually I ripped from this paper that actually I think is a really important thing to realize is that preventing the introduction of malicious code is not enough to prevent the execution of malicious computations. As defenders, what we're trying to do is stop malicious computations and malicious actions. Introducing new malicious code is only the most expedient way to do this, not the only way. And so we need to focus on the end effects, not the end strategy, not the tactics. So let's talk about how to do it the easy way, and I call this BISC. So this is just a Ruby library that demonstrates how to build borrowed instruction programs. Here's where I reference Sebastian Kramer and his, where he originally did this for x86-64 on Linux. So the main ideas I used here is, one, I wanted to keep it simple. I wanted to make it analogous to a traditional assembler, just to kind of fit into a more traditional workflow, and try and also minimize the behind-the-scenes magic and make a lot of what happens explicit to the user, because I was writing this for myself. And one, I can write x86 assembly. That's not hard. So I'm not scared of an assembler. And I want to make it explicit what I'm doing, so I'm not bitten with weird bugs. And then for convenience, I'll let myself write macros. And there are several ways that this differs from traditional or what's been called return-oriented programming. The key distinction is that return-oriented programming is actually, to be pure return-oriented programming requires a Turing-complete compiler. And my Bisq toolkit is absolutely not Turing complete because in your shellcode you rarely need conditionals, rarely need loops, so it actually is not all that necessary. And yeah, so again, this is just an assembler, and what it lets me do is write a borrowed instruction program with just assembly mnemonics that are found from the existing program. And so how it's going to work is first I run a scanner on a variety of code modules, and what these will be, well, these will be like the DLLs that I know are loaded at a certain place, or DLLs that are just available. Or for instance, if I can use a memory address leak, and then so I know that DLL X is at location Y, I can then scan it, assuming that version of the DLL is at location Y, so that my return-oriented program will execute correctly. And my ROP generator is very fast. It executes in a split second, so it's easy enough to just do in a Metasploit module. So basically, the way that the scanner works is I'm being fully transparent on just how ghetto this actually is. The secret to doing return-oriented programming fast is binary regular expressions. Because I don't care about looking for every possible instruction. I just care about finding a small number of ones that I need. And so what I did is I just took the instruction encoding for a variety of, just the standard arithmetic operations, data transfers like move, and a few others, pushes and pops and so on, and then basically combine those into a regular expression for the instruction encoding. And then I just have a loop, combines them all into one big regex, and it just scans the text segment and spits out everything it found, which is pretty nice because it's, one, fast. And one example is I used this on Mac OS X, the Mac OS X version of Google Chrome, which is a 37 megabyte text section, and it'll scan the entire thing in 5 seconds on like a relatively modern laptop. So that's distinctly what I call fast enough. So here's sort of how it works. If we run it on a arbitrary module, it'll just print out all of the things that we can use. And I call this our vocabulary. And if you look, you can see there's a couple interesting ones. We have an exchange EAX ESP. It's kind of useful. We have a move ECX into EAX. That's our memory read. We have plenty of memory writes. We have plenty of pops to set registers. And so we can say, all right, yeah, we definitely have enough workable pieces here that I can construct a meaningful payload. And the other thing that Bisq lets me do is, even though the stack unwinds upward, and so the memory addresses will go up, I want to write my program downward, just like a traditional assembly program, so that ideally I can look at the assembly and I'll understand it, because even though I won't be using the same instruction mnemonics that you would if you're just writing normal assembly, I'll be doing things in a similar way, so if I understand assembly, I understand what my program does just by looking at it. And one of the things to keep in mind is that you'll occasionally have to do workarounds. Because you are being very opportunistic on what instructions are actually available, you might not have the exact instruction that you need, so you will have to string together a sequence of instructions that are available that perform the equivalent function. So if you look at the bottom of the screen here, you can see on the right, I really wish I could just add 3 to memory pointed to by ECX. But unfortunately, that instruction, let's assume that instruction wasn't found. But the ones on the left were. And so I can say, all right, well, let's read from ECX into EDX, let's add 3 to it, and then let's store it. So it's a little bit roundabout, but it achieves the exact same thing. And so basically, I just write this as a Ruby library and kind of have this like intermediate language sort of syntax where my program is just an array. And elements in the array, if it's a string, that string gets looked up in a hash table to replace it with a memory address of that instruction followed by a ret. So keep in mind that I'm only looking for instructions followed by a ret. So whenever you see like a pop EAX, that'll be replaced with the memory address of a pop EAX ret. And another thing I forgot to point out is that I look for only very simple forms of instructions. If you looked at the x86 instructions, encoding and all this stuff, there's a lot of really wacky encoding types with prefixes, scale index bytes, displacements, all this stuff. And in order to make this simple, I just did away with that. So I only look for no displacements, no scale index bytes, no prefixes, just the bare instructions that I need, and that's actually usually enough. And when the day comes that that's not enough, I'll actually implement, add more functionality to the scanner to make it work. So these arrays also can be nested. So the nice thing about this is that it lets you write macros as just functions that'll return an array, and then that array gets embedded, and like the assembler just flattens it and assembles it. So it's pretty easy. And the macros let you write what I call higher order BISC. And if you think about how to do this, macros are like virtual methods for common high-level operations. And what you're going to do is you're going to write macros for like, my macros are kind of analogous to gadgets in return-oriented programming. And these will be things like set a variable to a value, do an arithmetic operation to a variable, so on. Call a function through a variety of ways. And what you do is you write your return-oriented program in terms of macros, not direct instructions. And so then if you retarget the generator to a different DLL, it may complain that certain instructions aren't found. And what you do is you just re-implement the macros until you have all the macros that you need, and you now have your return-oriented payload against that certain DLL. So it's manual, yes, but it takes like a half hour. I don't care. So here's an example of how a macro works. I just make it a simple Ruby function, and what it does, it returns an array of the instructions that it needs, and with the values in line, because those values get turned into 32-bit constants, and just returns the sub-program that implements that operation, so you can call it from your main program. So here's kind of a full example. Include the library, initialize the object. And I have the example macro called clear that you can see does a very roundabout way to set a memory address to 0. And so down at the bottom, I made it really hard to read just to make sure everyone was paying attention. You can see main equals clear v. And that main equals array is the main program. And it just basically says call clear, which returns those array elements, and put it in the array. So I can just write clear, comma, then more instructions, comma, another macro, and so on. And then finally, I just call assemble on it, and that'll just do the magic. Well, it's not really that magic. Give me the binary blob that I can just lay down on the stack to actually execute this. So this is intentionally uses the simplest implementation possible. 1, because I wanted to get it working that weekend. 2, because I wanted to actually show that it doesn't require heavy lifting, at least on x86 and Windows, to do this. And just to give people an adequate or accurate description of what level of defense ASLR and DEP provide on rich client-side applications, where attackers have a large, what I call control surface. Applications like this, where an attacker can run JavaScript, can run plugins, all this cool stuff, there are a gazillion avenues to possibly fix memory at one location, or learn where memory is at another, learn where other memory is at another location, and so that makes DEP and ASLR much less effective. So this, that's what I wanted to show with this. If you want to see how to do ROP in totally fancy way, you should have gone to the Dynamics talk yesterday, where they have much more academic and much cooler, in my opinion, treatment of this for ARM, in particular for iPhone. So let's talk about, so now we know kind of how to generate return-oriented programs. What are we going to do with that? And the main strategy we're going to use is actually a bridge to execution of a traditional payload. This is like a payload stage. And there's a couple things we can do. One, if there's executable memory at a known location, we can just copy our payload to that memory and then jump there. Or what we might need to do is allocate new readable, writable, executable memory and then write the payload there as well. An important thing to keep in mind is even permanent DEP doesn't prevent you from allocating new executable memory. If it did, things like JIT would break, and no one likes, no one wants to break Java. Another approach you can use is the write process memory trick, which I'll kind of talk about as well. Another cooler technique is building your payload in executable memory piece by piece. If there's if you can reuse existing data bytes, copy those to the executable memory, and have them assemble into your next payload. So it's kind of cool. Or you can just do the simple trick of, if your payload's in non-executable memory, you can just make that executable and then execute it from there. And so I'll kind of show you how this bypasses DEP. How DEP works on x86 is it uses an extra bit on the x86 processors to actually say, no, I really want this page to not be executable. And I kind of refer to this as the I mean it bit, because the operating system, if you look at a debugger, if you look at various other things, the operating system may say that a page is not executable, but unless in the page tables this bit is actually set, the processor won't enforce it. So this is the I mean it bit. It also requires that all modules be compiled with the nxcompat flag. And yet there's even more conditions. So even if you have all this, with the original dep, you could basically just turn it all off with a function called ntSetInformationProcess. And so Scape and Skywing showed just using one simple return to libc jump, they could just turn it off and then return to their payload, done. Dep is not that big of an issue. So XP Service Pack 3, Vista, and later support permanent dep, which cannot be disabled at runtime. However, permanent dep requires applications to specifically enable it in many cases. So for instance, if you run IE7 on Vista, like Vista SP1, which has permanent dep, it won't opt into it. You need to run IE8 on supporting operating system to actually use permanent dep, where you can't do this 5-year-old trick. So here's an example of just one way to, one stage you can do this, or one example stage that will enable a traditional payload. So yeah, like I said, depNX prevents execution of data, but it doesn't prevent you from making new executable code. If you look at something like Apple's iOS that runs on iPhones and iPads, they actually have a code signing enforcement where you're not allowed to do this. If you try and allocate new executable memory, the kernel will know that that didn't come from a binary that was personally signed by Steve Jobs, so it won't let it run. Whereas on Windows, sure, anything goes. So here we're going to go through 4 basic steps. First, you need to get your stack pointer. You need to find out where you're executing from, because we're going to need to patch up memory a little bit. And then we're going to allocate some more memory. We're going to copy our payload in, and then we're going to actually jump to execute it. So it's been at least like 10 minutes since I showed a stack diagram, and I know you're all waiting anxiously for the next one. So here you go. You can all relax. So this is what I call my get ESP. It's not really a gadget. It's kind of a gadget, which will get the location of ESP and store it. So first thing we'll do is retrieve a memory address that we're going to store it into. We're going to use my favorite exchange EAX ESP because it's very commonly available, and then store it. Boom. We now have a location in memory that stores our value of ESP, and I'll show you why we actually care later. So we need to, if we need to allocate some memory, I think that's actually the wrong comment. Oh no, that's the right comment. Basically, one of the tricks we're going to use is if we want to call a standard library function and there is ASLR, we can't just jump to the location in kernel32.dll, because that might be at a random place. However, if we know where DLLA is and DLLA imports one of these functions, we can just pull it out of the import table and call it through that. So that's exactly what we're going to do. So we just use the address of that DLL's import of the function that we want, which is virtual protect, in that DLL's import table. Read it, return, then we actually call it and jump to it. And basically what it's going to do is we need to kind of give it some arguments. Or actually, we call it virtual allocate to actually get some memory, and now we're actually going to store it. So we need to set the memory address we want to store it in, store EAX into it, and boom. We now have a pointer to readable, writable, executable memory. Now we need to copy our payload from where it exists into that memory. So this is why we actually retrieve the value of ESP. That lets us embed our traditional Metasploit payload or whatever right in the stack, or our fake stack, so that we can pull it out. So we did our get ESP so we can figure out where that payload is. So we load up that variable that we created with the pointer to our ESP, load that up, and now we need to calculate the offset from where we're executing to basically to actually this is where it's a little complicated. We need to have a dynamic argument. So we need to actually calculate the offset from where we're executing to where the argument will be on the stack. So I'll write down something like dead beef, and then in the fake stack frame to call the function, and then I will just overwrite that so I can clearly see that. So we calculate the offset here, we add the offset, load up our memory location, and then write it directly onto our stack to allow us to call a function with a dynamic argument. And we're going to do a similar thing to actually get the location of our payload. So grab the location of our memory, do the similar kind of song and dance to kind of find our argument, and then find the offset to our payload, and we're going to call memcopy. Now we have copied our payload into executable memory. All we need to do is set ECX to the pointer that points to it, dereference that, do a push ret, that'll just simulate a jump right to it, and we now have our payload running. So there's a couple variations on this. One thing we can do is like Pablo Soleil mentioned this in his presentation a few years ago. We can create a new heap with the flag heap create enable execute, and we can do that. So because we're calling things to the import table, if for instance virtual allocate isn't available from the module that you know, but heap create is, you can just do this. The other one is if virtual protect is available, you can just point that to your stack and do that, and just make your stack executable. And that's kind of actually a lot less code. Some other alternatives that work in non-ASLR environments were documented by Spencer Pratt, of all people, on Full Disclosure a few months ago. And he had an interesting write process memory technique. So write process memory does an interesting thing. In the spirit of being a little more user friendly, if the page you're trying to write to isn't actually writable, it'll make the page writable and then write the data to it. And so and another thing you can do is write process memory is traditionally used when you're debugging another process. Well, you can just pass an argument to it that specifies this process. And so you'll just use these debugging functions on yourself. And the key to the trick here is that the data that you're going to overwrite is the code for write process memory itself. So what happens is, at the function prologue, right after write process memory has finished writing the data, and it expects that it's going to return, it's now going to execute the code that you've just slammed there. And because most applications won't use write process memory, the fact that you've obliterated its code and kind of made it useless will not affect the application. So that's kind of a cool trick. But it gets kind of cooler. He called it the seance technique. So if you don't know the location in memory of your shellcode buffer, which is also common because that's why we had to do the get ESP to kind of find where we were. So if you don't know that, you need to do something else. But you do know where write process memory is because kernel 32 is at a fixed location on a non-ASLR system. What you can do is chain a sequence of returns to write process memory to build your shellcode in an existing text segment. So you can find some space at the end of kernel 32, for instance, and then find a couple bytes from here, a couple bytes from there, 3 bytes from there, and then just keep using write process memory to copy them there and go blip, 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 and build your entire payload that way. And that's kind of cool. Another variation on this is I call it the bring your own borrowed instructions technique, where what you do is instead of building your next payload, you just write so like I said, with the borrowed instruction program, you don't have all the instructions that you need. What you can do is you can copy those bytes to build the instructions that you need in executable memory, and then use those to write the return-oriented program that you wish you could. So that's kind of fun. So now, if you look at kind of the pieces that I've talked about, we have the stack pivot to use control of EIP to get control of ESP. That's the stack pivot. You have a return-oriented payload stage that'll bring you to executing a traditional payload. And you have a Windows payload. You just grab that from Metasploit. You now can bypass permanent dep with an arbitrary exploit. So that's pretty cool. So let's see how to actually do this in practice. So the Aurora vulnerability on Windows 7, everyone knew about this. The internet was destroyed, blah, blah, blah. Google actually was on the first big companies to actually admit publicly, hey, we've been hacked. We all work in information security. We know a lot of these places have been hacked, but no one can talk about it. But Google said, yeah, we got owned pretty bad, and it sucked. So that's actually kind of a big step, and actually I think will help move the industry forward a bit. But let's talk about the details of the vulnerability here. So the root of the vulnerability was that there was, in MS-HTML, there was an event param object. And what this object did is this encapsulated the state for the JavaScript event objects. And there was a JavaScript function called create event object, and if you passed it a template object to copy, it would not increment a ref count to an object called a ctree node. And so the way that MS-HTML kind of represents the DOM is basically there are C elements and C tree nodes. And so the C element represents the actual HTML element, like the HTML tag and all that stuff. And the C tree node just represents its position in the DOM tree. And that lets them kind of move things around the tree more efficiently. And so the event param actually had a point, a lot of objects don't point directly to the element, they'll point to the DOM tree node, which will point to the element, and they kind of reference each other. So event param would have a pointer to the seed tree node, but because it didn't increment the reference count, I use a dotted line here, because instead of being a strong reference, it's a weak reference. And that actually will result in, problems. Yeah, so this is basically what I said here. We have the event param has a weak reference to the seed tree node. And the C element also points to the seed tree node. So we have two pointers to the same C++ object, but only one of them is reference counted, the other isn't. So if you wrote JavaScript to remove the HTML element, that the corresponding HTML element from the DOM, what will happen is the C element object will get freed, and then in the process of doing so, it'll see that it has a pointer to C tree node, and it will decrement the reference count to C tree node. And what you have there is that the C tree node reference count becomes 0, and so when the reference count is 0, the object gets freed, and event param still retains a pointer to freed memory. And this is the classic use after free vulnerability. So if an attacker can actually use controlled heap allocations, they can replace the freed block with a crafted heap block. And this is actually amazingly easy. Heaps heaps on modern operating systems are very deterministic. And because what you're doing is you're exploiting this in JavaScript, all you need to do is look up what the size of that C tree node object is in memory, and then just do a bunch of memory allocations of that exact size. And if you do, usually in the first few, the Windows heap will return that same memory that the event param still points to. And in doing so, if you now have a pointer or a way to operate on that object from JavaScript, and you have a stale reference to it. And actually one of the harder things to find is not just the way to allocate this object, but a way to allocate this object that gives you full control over it. And so the trick is, at least for this vulnerability, was we needed to control the C++ vtable, which is in the first 4 bytes. And so if you think of the first thing that comes to mind of how are we going to allocate this object, the first thing that comes to mind is we'll just use a JavaScript string. The problem with that is in JavaScript strings, the first 4 bytes are the length, and so that's obviously not going to help because we're getting the length to be equal to the address of our fake vtable on the heap means we're going to have a huge string. So we're going to try and find something else. And so if you go through IE, you can find a number of places where they do memory allocations that do let you control both the size and the full contents, the first 4 bytes and the rest. And so once you do that, you can have a fully crafted C tree node object. So you just cause that allocation, override it with custom data, and you now have controlled the full C tree node. What we do with that is, for I'll call it just a simple naive exploit that uses like a heap spray, we're just going to point that into the heap spray. So that address, the 0C, 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 sort of the common, I've sprayed the heap, there's a bunch of stuff there. And so our crafted C tree node will have a fake vtable pointer, or sorry, crafted C tree node actually has the pointer to the C element. The C element has the fake vtable, and basically what we do is we just kind of have a self-referential data structure here. And because we've sort of laid everything out in the heap, we can kind of use, and we use sort of a standard block size. We use different offsets within that block to represent different pointers. And so that lets us have a pointer to an object and it points to another object and another object, and it all just sort of it's all sort of crammed into the same memory, but we just need to make sure that the pointer dereferences actually work out. And finally, when we have the element that is that represents the fake vtable, what it's going to have is the vtable pointer that gets used is going to be our stack pivot. And so in this exploit, we use the exchange EAX ESP stack pivot. And because when a C++ code calls a vtable, at least in this code, it would load the vtable into EAX and then do the function call. So EAX pointed to our heap sprayed memory. And so then we do the stack pivot, and then what happens then is our stack pointer now points to the heap spray, and we need to make sure, since we put a lot of pointers there that are self-referential, we need to make sure that we don't try and return to that pointer in a way that'll just make things crash. And so I just put in some addresses of, like for instance, the address of a pop ret we can use to skip over pointers. And then once we skip over that, we can just put the address of a return instruction, and that kind of functions as a pseudo nop. I like calling it a ROP nop just because it sounds silly, but that's basically what it does. It lets you build like a ROP nop slide or a ROP nop sled. We got to figure out better terminology for this because it's actually really silly. And so basically when we do this, it goes straight to our ret sled, and right at the end of that, after a sufficient amount, have a return-oriented payload stage, which is very much what I demonstrated earlier. So then that payload stage actually just goes through and does all that stuff I talked about before, executes our Metasploit payload, boom, we win. So let's actually see what that looks like. All right, we're going to load up. All right, cool. All right, so basically what I have here is just okay, cool, it's loading. Simple web page. My exploit is written in JavaScript. So what that means is I just have, actually I can show you here. Make sure to show you the man behind the curtain. Load a JavaScript file. When I click run exploit, runs main. Main does a whole bunch of magic. So, you ready? Usually I make a comment to this part of my presentations about making a sacrifice to the demo gods, but this time I didn't do that, so I'm going to run flagrantly in the face of the demo gods and see if this actually still works. Okay, cool. Got a calculator. So, and then we can close it, and well, we can get another one. We can kind of do this as many times as we want. Oops. Because actually in the future, when everything is on the web, we won't actually have desktop calculators. And if we want to launch one, we'll have to go to an exploit web page to actually run one for us. So that's how that works. All right, back to the presentation. That is not what I wanted to do. See, I can own IE8, but I can't operate PowerPoint. All right, so let's draw some conclusions from this. So one of the key points I'm trying to make is we need to have an accurate depiction of what our exploit mitigations actually provide us. And to be fair, DEP and ASLR do a great job of protecting server-side vulnerabilities, or mitigating server-side vulnerabilities, because you have a much less control surface. And so that's what they were designed for, and that's what they work very well on. On client-side applications, because you have a lot of different code bases in the program, it's a little trickier. So if you have no ASLR, all your exploitation requires is building a reusable return-oriented payload from any common DLL. So you can choose any one, like on Windows XP, if you're looking at IE8 on XP Service Pack 3, you can just choose any one that you like. I have my favorites. I'll let you pick your own. If you have an ASLR system that has one or more modules that does not opt into ASLR, all you need to do is find which one that is and solely use that for your return-oriented exploitation. And this may require a variety of strategies. You can do a little bit of ROP, a little borrowed instructions, a little bit ret to libc. You kind of have to mix and match often to get what you need. But one thing you'll find is if you look at a lot of common plugins and even a lot of common web browsers, there'll be one or two DLLs that still don't opt fully into ASLR. So if you just bring them up in a debugger, you can usually find them. So if you're in the situation where all modules opt into ASLR, well, it's a little trickier. What you're going to need to do is find a memory address disclosure vulnerability to actually reveal the address of a DLL and then use that to build your ROP stage and execute that. And if you want details on how to do that, you can read a paper by Peter Grundlehill, who won Pwn to Own this year. And he described his technique where he found, if I recall, an issue where you had a non-null terminated string. And what he could do is he could allocate that on the heap and do a little heap manipulation so that the string would be allocated right before a C++ object. And then when he read the non-terminated string, it would actually bleed into the next heap object. And the first thing he'd see would be the C++ vtable of another object. Well, the vtable pointer points to the text segment of a loaded DLL, so he could read that vtable from JavaScript. So now he knew where a DLL that he knew the type of, or he knew that DLL X is at location Y, and he could use that to rebuild his return-oriented exploitation stuff, to retune his exploit and go. So the point is that if you have full ASLR, you now need kind of two vulnerabilities to get code executing. And what this does is, keep in mind, you do not need malicious code to do malicious computation. And the mitigations do a pretty good job of making this more difficult. But overall, we still don't, and desktop applications in particular, we still don't have enough, in my opinion, separation, privilege reduction, and all this stuff. Because once you get code executing, if you look at like IE8, you're executing in low integrity mode. So low integrity mode doesn't let me write to any files outside of certain locations, but it's enough to run a calculator. It's enough to read all your sensitive data. If you happen to be a computer on a network, which you probably are if you're getting exploited over the web, you can still go over the network as that user. A lot of things you can do that you do not necessarily want. So that's not exactly as thorough a privilege reduction as something like Google Chrome Sandbox, which has is increasingly restrictive. And if you looked at Tavis and Julian's talk earlier today, even in environments like that, you still have a wide open kernel attack surface that you might need to actually break out of that. And what we're seeing is that which is a good thing, now to have a meaningful client-side exploit, you need to chain together multiple vulnerabilities to actually really do damage. And that'll actually put us in a better place, because otherwise, one exploit ruins your day, and you're cleaning up infected machines and someone with all your IP and all this bad stuff. So I think we need to kind of think more about how we can structure our applications in a way that'll contain that flow, because as we've seen, firewalls contain and reduce the attack surface on the network. We don't have that option for client-side applications. We can't turn off the sketchy functionality in, Adobe Reader, IE, Firefox, whatever, as a user. So that's my last bit of rant. Now I'll open up to questions, and you can ask questions now, email me, follow me on the Twitterverse, hit my webpage, whatever. So are there any questions? All right. That makes it really easy. Cool. All right. Have fun. Thanks.